For this question, it's helpful to set up the chemical reaction as described and then determine the changes that occur when the chemical reaction occurs. Let me show you. So we have this particular reaction of N2O5 going to NO2 and O2, and it is a first-order decomposition reaction with a rate constant of 7.48 times 10 to the negative 3 1/2 seconds. You'll notice that it is not balanced, so we have to balance it by putting a 2 in front of the reactant and then a 4 in front of the NO2 product. This then gives us 4 nitrogens, 8, 10 oxygens, and 10 oxygens. So if we start with a solution that is 0.1 atmospheres of N2O5, as this reaction occurs, we will decrease the pressure of N2O5 and increase the pressure of the products. I'm going to represent the change with an X value and the magnitude of the change with the X being multiplied by the coefficient. So dinitrogen pentoxide will decrease by 2x, where nitrogen dioxide will increase by 4x and oxygen will increase by x. So at any given time during the reaction, these will be the pressures associated with the reactant and products. So the total pressure at any given time will be the sum of all of these pressures. You'll notice that we get 0.100 minus 2x plus 4x, so that's plus 2x plus 1 more gives us plus 3x. So the total pressure will always be 0.100 plus 3x. So if we have a total pressure of 0.145, then we can solve for x at this particular moment in the reaction, where x will be equal to 0.015. So the pressure of just the reactant at that moment will be 0.1 minus 2 times x that we just determined, or 0.070 atmospheres. Now, because we know it's a first-order decomposition reaction, then we can calculate the time that is required for this pressure to be reached using the first-order integrated rate law. Natural log will be equal to 0.070, the pressure that we desire, divided by the initial pressure, equal to negative k, multiplied by t, and we can solve for time. And the time required to give us a total pressure of 0.145 will be 47.7 seconds. Now, to solve for the time required for a total pressure to be 0.200, we'll do the same calculation that we performed here, but plug in 0.200, solve for x, and then using x, solve for the pressure of the reactant at that time. Then, using the pressure of the reactant at that time and the initial pressure of the reactant with the first-order integrated rate law being the natural log of the pressure at time t divided by pressure at time 0 equals negative kt, we can solve for t, or time, as we did down here, and we get 147 seconds. Now for part C, it wants you to find the total pressure after 100 seconds. So to do that, we first need to find the pressure of the reactant after 100 seconds. We'll again use the first-order integrated rate law, slightly modified, where the natural log of the pressure of the reactant at time t will be equal to negative kt plus the natural log of the reactant at time 0, which is 0.100. This gives us the natural log of the reactant at time t being equal to negative 3.05, and if we take the anti-natural log of both sides, we get a pressure of the reactant of 0.047 atmospheres. So the total pressure, as shown up here, will be 0.100 plus 3x, and x, well, hold on a second, x, I'm using the variable to define two different things. This x is just the pressure of N2O5, so I need to use the pressure of N2O5 to solve for x. And remember, the pressure of N2O5 is always going to be 0.100 minus 2x. So the pressure of N2O5 equals 0.100 minus 2x, and I can get x for the process after 100 seconds. Then knowing x, I can go back up to this expression where P total is equal to 0.100 plus 3x and solve for the total pressure, which is 0.179 atmospheres.